In the previous video, we saw some steps for drawing dot structures. In this video, we're going to use those same steps to draw a few more dot structures, but we're also going to talk about how formal charge relates to dot structures. So we'll get back to this definition in a minute. For right now, let's draw a quick dot structure for the ammonium cation, so NH4+. The first thing you do is find the total number of valence electrons. And so to do that, you look at a periodic table and find nitrogen, which is in group 5. Therefore, nitrogen has 5 valence electrons. Right? Each hydrogen has 1, and we have 4 of them. So we have 5 plus 4, giving us 9 electrons. However, there's a +1 charge, meaning this is a cation, meaning we're going to lose an electron here. So instead of representing 9 in our dot structure, we're going to represent 8 electrons. And so let's go ahead and put the nitrogen at the center. Remember, we put the least electronegative atom at the center, except for hydrogen. So nitrogen is going to go in the center here, and we know it's going to have bonds to 4 hydrogens, so we go ahead and put in those hydrogens right here. And let's see how many valence electrons we've used up in our dot structure. 2, 4, 6, and 8. So that takes care of all 8 valence electrons that we were supposed to represent. So this is the dot structure. And I can go ahead and put some brackets around it here, and also a +1 charge to indicate that this is an ion. And so that's the dot structure for the ammonium cation here. Let's see if we can assign formal charges to the nitrogen and the hydrogen. So I'm going to go ahead and redraw our dot structure here, and I'm also going to draw in the electrons, right? We know that each of those covalent bonds consists of 2 electrons. Let me go ahead and put in those 2 electrons right here. And if I wanted to find a formal charge for, let's say, the central nitrogen, right, what I would do is think about the number of valence electrons in the free atom. So if you had a nitrogen all by itself, right, you look at the periodic table, it's in group 5, and so therefore we're talking about 5 valence electrons in the free atom for nitrogen. From that number, we're going to subtract the number of valence electrons in the bonded atom. And the way to approach that is to look at your dot structure here and think about those 2 electrons in those covalent bonds, right? One of them we're going to assign to the hydrogen, and one of them we're going to assign to the nitrogen. And so we go around, we do that for each one of our covalent bonds like that. And so now we can see that nitrogen is surrounded by 4 valence electrons in the bonded atom. So let me go ahead and write that. So it's 5 minus 4. And so 5 minus 4 is, of course, +1. So we have a +1 formal charge on the nitrogen. So this nitrogen has a +1 formal charge. Now let's do it for hydrogen here. So hydrogen's in group 1 on the periodic table. So let me just point this out. This is for nitrogen. And then for hydrogen, right, it's in group 1, so 1 valence electron in the free atom, and from that we're going to subtract the number of valence electrons in the bonded atom. So if we look here, right, we assigned 1 valence electron here to each hydrogen, so therefore it's just 1 minus 1, or 0. So there's 0 formal charge for all of the hydrogens in the ammonium cation. And so that's how to assign formal charges. Let's see how that applies to actually affecting our final dot structure, and an example of that would be something like sulfuric acid here. So the first step, of course, is to calculate the total number of valence electrons we need to worry about in our dot structure. So once again, each hydrogen is 1, and I have 2 of them. Sulfur is in group 6 on the periodic table, so therefore it has 6 valence electrons. Oxygen is also in group 6, and so we have 6, and we have 4 of them right here. So 6 times 4 is 24, right? So we have 24 plus 6 is 30, plus 2 is 32. So we need to worry about 32 valence electrons in our dot structure for sulfuric acid. All right, next thing we need to do is choose the central atom. And once again, you ignore hydrogen, so it's between sulfur and oxygen. And if you look at a periodic table, you will see that oxygen is higher in group 6 than sulfur is. Therefore, oxygen is more electronegative. And so therefore, we're going to put sulfur at the center, right? So we're going to put sulfur right here. And once again, look at the rules from the previous video, if that didn't make quite sense to you here. So we have sulfur attached to 4 oxygens. I'm going to go ahead and put my 4 oxygens in there like that. And then I have 2 hydrogens. And by experience, you're talking about an acid here. You're going to put your hydrogens on oxygens. And so we're going to go ahead and put our hydrogens here. And let's see how many valence electrons we've used up drawing this skeleton here. So we have 2, 4, 6, 8, 10, and 12. So we've used up 12 valence electrons, so 32 minus 12 gives us 20 valence electrons left to worry about. And so remember, the next step is to assign some of those leftover electrons to some of the terminal atoms. But again, we're not going to assign those electrons to hydrogen because hydrogen is already surrounded by 2 electrons. And so we're going to try to assign some electrons to oxygen, and oxygen is going to follow the octet rule. So let's examine, let's say, the top oxygen here, and we can see the top oxygen is surrounded by 2 electrons already, right there in green. And so if we're going to give it an octet, it needs 6 more. So we have 1, 2, 3, 4, 5, 6. Same thing for this oxygen down here. It needs an octet, so we go ahead and give it 6 more electrons like that. Right? So we also have these other oxygens over here to worry about. So let me go ahead and use green again. So let's say this oxygen over here on the left, the one bonded to this hydrogen, here's 2 electrons, and here's another 2 for 4. So for that oxygen to have an octet, it needs 4 more. So that means we're going to put 2 lone pairs of electrons on this oxygen, and then we're going to do the same thing for this oxygen as well. So let's see, how many electrons did we just represent there? Well, we had 6 on the top oxygen, 6 on the bottom oxygen. That's 12. And then we had 4 on the left and 4 more on the right. So that's 8. So 12 plus 8 is 20. So we've now represented all of the valence electrons that we needed to show. And let's think about this as possibly being the final dot structure, right? So we have an octet around sulfur, we have an octet around oxygen, and hydrogen's fine. So you might think that we are done here. However, let's go ahead and assign some formal charges, and let's see what that does. So let me go ahead and draw in some electrons here. So we know that each bond consists of 2 electrons. I'm going to go ahead and make them red here, like that. And let's assign a formal charge to the top oxygen here. Right, so this top oxygen, right, I'm going to, in the bond between oxygen and sulfur, I'm going to give 1 of the electrons to oxygen and 1 of the electrons to the sulfur, right, and so I can see that oxygen is being surrounded by 7 electrons. In the free atom, right, we would expect oxygen to have 6 valence electrons. 6 minus 7 in this case gives us a formal charge of -1, and so this top oxygen has a formal charge of -1. It's the same situation for this bottom oxygen here, so that one has a formal charge of -1 as well. Let's look at the sulfur. All right, so if we examine the sulfur here, and we know, right, sulfur's in group 6 on the periodic table, so normally 6 valence electrons for the free atom. And in this bonding situation, right, let's go ahead, we know this one oxygen goes, this one electron, I should say, goes to sulfur, and then in this bond between oxygen and sulfur, sulfur's going to get 1 electron, and so on all the way around here. So sulfur is surrounded by 4 electrons in the bonded atom here, and so it's 6 minus 4, which is a formal charge of +2. So this dot structure might look like we're done, but we have a lot of formal charges, right? We have -1, +2, and -1. And usually molecules like to minimize the formal charge. And so if there's any way to get this formal charge as close to 0 as possible, that would be the preferred dot structure. And so let's go ahead and redraw this really quickly, and let's see if we can move some electrons around to minimize our formal charges. Now, we can't add any more electrons because we've already represented all 32 valence electrons that we were supposed to. So the only thing that we can do is to share some more electrons. And so if I took 2 electrons from this top oxygen here, so if I took these 2 electrons and I moved them into here, and if I took these 2 electrons right here and I moved them into here to form double bonds, let's go ahead and look and see what our dot structure would look like and assign some formal charges. So now I would have sulfur double bonded to this top oxygen and double bonded to this bottom oxygen. Top oxygen has only 2 lone pairs of electrons around it. Same thing for this bottom oxygen. And then these oxygens are the same with the OH on the left, and then we have the OH on the right here. Okay, so now let's look at our formal charges. So we'll put in our electrons. So let's go ahead and do that. And once again, we're going to do the same thing that we did before. So assigning formal charges, we'll start with the top oxygen here. So the top oxygen, right, 6 valence electrons in the free atom, and then if I go like that, you can see there are 6 here. So 6 minus 6 gives us a formal charge of 0. So the top oxygen is 0 now. Same thing with this bottom oxygen. This one's 0. Let's look at the sulfur now, right? So normally we're talking about 6 for the sulfur, and let's see how many valence electrons are around the bonded atom here. So we do the same assigning of electrons that we've done before, and so now we can see that that sulfur is surrounded by 6. So we would go 6 minus 6 gives us a formal charge of 0. And if you assign a formal charge to one of these other oxygens, so let's go ahead and do that really quickly. So one of these other oxygens right here, so I'm doing the oxygen on the right. Okay, so let's see how many valence electrons are surrounding this atom. So we have a total of 6 as well. So 6 minus 6 is a formal charge of 0. So this dot structure actually gives us formal charges of 0 for everything, and so this would be the preferred one. And let's finally talk about octets, right? So we know that the hydrogen is happy surrounded by 2 electrons. We know that oxygen is happy with an octet, and so you can see that all of these oxygens have an octet. Sulfur, in this case, is not surrounded by an octet. It has an expanded outer shell, right? And it's okay for sulfur to have an expanded valence shell because it's in the 3rd period on the periodic table. And so we talked about why that's okay in the previous video. And so this is just one more thing to think of when you're drawing dot structures. Sometimes formal charge will affect the final structure of your molecule or ion.